If industrial shaft drive equipment, such as the motor and compressor shown here, are to operate efficiently and provide reliable long-term service, it is essential that the two shafts be aligned as close to perfectly straight as possible. If the shafts are even slightly out of line, energy consumption can increase dramatically, especially if the equipment operates under heavy load. If the degree of misalignment is more severe, however, destructive forces may be placed on the bearings, seals, and shafts of both the drive unit and the driven unit, and on the coupling which links them. There are, of course, flexible couplings designed to absorb slight misalignment, but they are not a substitute for good alignment practices. For years, industrial maintenance technicians have aligned shafts using mechanical measuring devices. But for many technicians, laser technology is rapidly replacing the older, more conventional tools.
Would you like to do your job easier? Number one, that gets their attention. Number two, I can back it up with facts. Instead of sitting there for days on end, scratching your head, worrying about indicator bracket sag and all this other stuff, I can hook you up and have you out of there in just a matter of hours with a perfect alignment. And people really enjoy that aspect of it.
It's more precise. It makes it easier for you to align it because it has a step-by-step procedure. You go from one step to the next step. It's all self-explanatory through the program with the laser alignment kit.
Laser alignment is gaining in popularity because it is simply more precise than other alignment methods. And precise alignment very often translates into longer part life, more reliable operation, reduced noise and vibration, and energy savings many times greater than the cost of the laser equipment. Best of all, the laser method will prove much faster and easier than conventional methods once the technician is familiar and comfortable with laser alignment procedures.
Yes, laser alignment on something that would have taken you 2 hours now only takes you anywhere from an hour to an hour and 30 minutes. So laser alignment does cut down your time.
Started out, we can normally do a complete alignment in an hour or less, whereas opposed to dial indicators, it would run anywhere from, I have seen them go as long as 3 days and still be working on it.
In this program, we will take a detailed look at laser alignment. We will quickly review some basic principles of shaft alignment and then more closely examine the principles of laser alignment. We will establish some important safety precautions, describe the preparation of equipment for alignment, and then examine an 8-step laser alignment procedure. Couple shafts are said to be aligned when their long axes lie along the same straight line. Shafts can be misaligned in 3 ways. First, parallel misalignment occurs when the long axes of the shafts are offset. They lie along parallel lines, but one is above, below, or to one side of the other. They are not lying on the same center line. Second, angular misalignment occurs when the long axis of one shaft crosses the long axis of the other. And third, combination misalignment indicates the presence of both parallel and angular misalignment, and certainly this is the usual case. The computer simulation shown here demonstrates the stresses combination misalignment can place on equipment. The left and right movement of the shafts is typical of parallel misalignment, and the flexing visible in the base of the unit suggests angular misalignment. To combat misalignment problems, 3 common methods for shaft alignment have been developed. The straight edge and feeler gauge method is the oldest and perhaps still the most common, even though it is the least accurate of the 3 methods. The dial indicator method is more accurate than the straight edge and feeler gauge method, but not as accurate as the laser method. The laser alignment method is the most accurate of the 3 and often requires less than 1/2 the time of the dial indicator method. A portable computer performs all the necessary calculations for the technician. There is no straining to read the dial indicator in a difficult position. The laser equipment is easier to attach, and it eliminates bridging devices and any problems caused by hardware sag. But perhaps the most important feature is that laser alignment equipment works with the shafts coupled or uncoupled. Alignment can now be quickly and easily checked, perhaps as part of a preventive maintenance program. And the alignment can be checked while the equipment is at operating temperatures, which makes the check most conclusive. To understand the use of the laser alignment equipment, it is helpful to understand the equipment components and how they work. Of course, different manufacturers offer different designs and features in their equipment, but many of the operating principles are very much the same. In general terms, laser alignment equipment consists of three primary components: a handheld computer, mounting brackets, and two laser optical devices, which we'll refer to as optic heads for now. The computer receives information from both the technician and the optic heads. It uses the information to determine the type and extent of misalignment and then to calculate the necessary corrections. The computer may be connected by a wire to one of the optic heads, or it may receive an infrared signal, in which case a hardwire connection is not necessary. In some situations, however, the infrared signal can be easily lost, so a lightweight external receiver may be provided to improve signal reception. The brackets are used to mount the optic heads on the shafts of the two units. Belt or chain brackets are most common. However, sliding magnetic brackets may be used when one or both of the shafts cannot be rotated. When using sliding magnetic brackets, the accuracy of the alignment will be dependent upon the surface finish of the shaft or coupling to which the magnet is attached. There are a variety of other brackets available to accommodate large couplings, tight situations, and other problem applications. Now, let's look at the optic heads. Although different brands of laser alignment equipment are quite similar, there may be one or two lasers in use. If one laser is used, the optic head which contains the laser is referred to as an emitter receiver, or perhaps a transducer. This device is mounted on the driven or stationary unit. It emits a beam of laser light which strikes the optic head mounted on the driver unit, often referred to as a reflector or prism reflector. The light is reflected back to a detector housed in the emitter receiver. During the alignment procedure, the computer will record the position of the beam on the detector with the optic heads in the 12 o'clock position and use this position as a reference. The computer will then compare the original position of the beam to the position of the beam when the heads are in the 3 o'clock, 6 o'clock, and 9 o'clock positions. Tiny changes in the position of the beam are used by the computer to calculate misalignment values and the necessary corrections. If two lasers are used, both optic heads will contain an emitter and a detector. A prism reflector is not included. Before moving on, we will quickly introduce some secondary components you may encounter. For example, some laser alignment equipment employs an invisible laser. There may be included with the equipment an electronic wand known as a beam finder. On this particular finder, lights change from red to green to indicate the beam is centered between them. The beam finder can prove helpful when first installing and adjusting the optic heads. You will precisely adjust the position of the beam on the detector during the alignment procedure, but you have to get it there first. Another device you may encounter is known as an inclinometer. It works like a carpenter's bubble level to indicate the 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock positions of the shafts, telling you when the proper measurement positions have been reached. If the alignment is to be performed with the shafts coupled, only one inclinometer is required, and it is usually attached to the mounting bracket of the optic head on the driver unit. If the shafts are to be uncoupled, a second inclinometer is attached to the bracket on the driven unit. Some alignment equipment does not require inclinometers, however. Instead, the computer automatically senses the orientation of the optic heads and displays their positions. As with any job, safety is the most important part of laser shaft alignment. Most important, never work on shafts or couplings without first locking out all related equipment. There are also some specific safety precautions to be observed when working with laser equipment. The word laser means light amplification by stimulated emission of radiation. And laser light has several properties which make it different from normal light. Light such as that from the sun, although powerful, spreads out as it travels. Laser light, on the other hand, travels in a parallel beam and spreads out very little. In addition, sunlight is a combination of many different colors of light, each with a different wavelength. Laser light, on the other hand, has all wavelengths filtered out except for one. The light beam emitted is a very powerful form of light known as coherent light. The precautions to be taken depend upon the class of the laser being used. There are 4 classes of lasers, which are designated simply Class 1, Class 2, Class 3, and Class 4. Only Class 1 and Class 2 lasers are used for shaft alignment. Class 1 lasers produce no known hazard to humans. They emit a low-power beam, which may be either visible or invisible. Class 1 lasers have been the traditional choice for alignment equipment, but some newer models are now using Class 2 lasers. Class 2 lasers produce a visible light, but in well-lighted and relatively dust-free environments, the beam may be difficult to see, as is the case here. But it is there nonetheless. Under current regulations, special eye protection is not generally required because momentary eye contact is not considered to be harmful, but only momentary contact. The light from a Class 2 laser is so bright that the natural aversion reaction should cause a person to look away or blink within a quarter second. This is not enough exposure time to cause permanent damage to the eye, but do not attempt to overcome your natural aversion to the light. If laser light is allowed to enter the eye, the lens of the eye will tend to focus the light even more. If the exposure is of a sufficient duration, retinal burning may result. The alignment procedure can be performed very safely by following 4 basic safety precautions for low-power lasers. First, never look directly into the laser light beam. When working with laser equipment, you should position your body so that you are not looking into or sighting down the length of the beam. Second, avoid mirror-like reflections of the laser beam. The beam can be reflected by any polished surface, and the reflected beam should be considered just as hazardous as the original. Third, limit the path of the laser beam. When rotating shafts with the laser equipment turned on, always rotate both optic heads at the same time so that the beam cannot escape. And do not operate the laser with only one optic head in place. A stray laser beam is a potential hazard. And fourth, read the manufacturer's literature. You should always be familiar with equipment-specific instructions and precautions provided by the laser manufacturer. The first step in preparing equipment for laser alignment is to check the bases of the units. Make sure you start with a solid foundation and that both units sit perfectly flat. Next, secure the driven unit, in this case, a compressor on an industrial chiller. You will probably have little choice in the placement of the driven unit, so it is leveled and bolted down first. The driver unit is adjusted to it. All 4 feet of the driven unit must rest firmly on the base plate. First, try rocking the unit, and then try to run a single thin blade of a feeler gauge under each foot. If there is any movement or any clearance, add shims until the driven unit is solid. Pre-cut stainless shims should be used if they are available. Do not attempt to stabilize the unit simply by tightening down the bolts. If the bolts are loosened, the unit will shift positions immediately. This condition is known as soft foot, and it makes accurate alignment impossible. Always check for soft foot in existing installations. The check may be performed manually with a dial indicator, or with some advanced systems, the computer will direct you to loosen each bolt one at a time so that it can check for soft foot. The shaft of the driven unit is normally set slightly higher than the shaft of the driver. During the alignment procedure, the driver is shimmed up to the height of the driven unit. If there is not sufficient height difference between the driven unit and the driver unit, the adjustments necessary to bring the units into alignment may not be possible. Before beginning the alignment procedure, check the shafts to see if they are running true. This check can also be performed with a dial indicator. If either shaft is out of specification, it must be replaced. Finally, the coupling should be checked for slack or backlash. If slack exists in the coupling, measurements may not be correct. If the slack cannot be removed, 2 inclinometers or the electronic equivalent must be used to ensure accurate alignment. With the equipment properly prepared for alignment, we are ready to begin the 8-step procedure. The procedure we will describe is typical of laser alignment equipment. Equipment, of course, will vary, but the basic steps should remain more or less the same. Let's begin by listing the steps. First, mount the brackets. Second, install the optic heads. Third, enter machine dimensions. Fourth, adjust the optic heads. Fifth, take alignment measurements. Sixth, display the alignment conditions. Seventh, display the corrections required. And eighth, adjust the driver unit. Now we'll look at the steps individually. Step number 1 is to mount the brackets which will support the optic heads. A word of caution, loose brackets will cause false readings. Tighten them securely. The second step is to install the optic heads on the mounting brackets. If only one laser is to be used, position the prism reflector onto the posts of the driver unit mounting bracket and the emitter on the driven unit. Be sure to install the heads with optics facing inward. Slide the heads as far down the post as possible while still providing space for the laser beam to clear the coupling. Connect the cable from the optic head to the computer, if one is provided, and secure the cable to the mounting bracket. The computer and the laser can now be switched on. If the computer does not come on, check the batteries and install new ones if necessary. Most computers will perform a systems check and report errors if any are present. Position the optic heads so that the light beam is striking the appropriate detector. This is when the beam finder may prove useful. Step 3 consists of entering certain measurements when prompted by the computer. These measurements can be obtained with sufficient accuracy using a tape measure. Some computers will ask for all measurements at once, and some will ask for the measurements when needed. Generally speaking, there are 6 measurements which must be considered. They are the distance from the back foot to the front foot of the driven unit, the distance from the front foot of the unit to the optic head mounted on it, the distance between the optic heads, the distance from the second optic head to the front foot of the driver, the distance from the front foot to the back foot of the driver, and last, the diameter of the coupling. Now, not all laser alignment equipment will ask for this exact list of measurements, but the list will be quite similar. Step 4, make final adjustments to the optic heads. Although they all work slightly differently, alignment computers will typically display X and Y coordinates representing the position of the beam on the detector. If the beam is centered, the coordinates will be 0, 0. The X coordinate represents the horizontal position of the beam. A thumb wheel or similar device on the side of the bracket or optic head should be turned until the X coordinate equals 0. The Y coordinate represents the vertical position of the beam. The Y coordinate is adjusted by carefully sliding the prism reflector up or down until the second coordinate also equals 0. We now have the equipment mounted and adjusted, and we are ready for step 5. Take alignment measurements. Measurements are recorded in the computer from 4 shaft positions. They are the 12 o'clock, the 6 o'clock, the 3 o'clock, and the 9 o'clock positions. Very often, 4 readings cannot be obtained because of obstructions. Most computers can use 3 readings and calculate the 4th. The measurements can be entered in any order, but we'll start at 12 o'clock. If you are using inclinometers, you will have to inform the computer that the brackets are at 12 o'clock. When you confirm your entry, the computer will take its initial reading. If you are not using inclinometers, simply command the computer to take the reading. Rotate the shafts 90 degrees and take a second measurement. Continue until at least 3 measurements have been taken. Step 6. Display the alignment conditions at the coupling. During this function, the computer will display the parallel misalignment present and then the angularity if angular misalignment is found. To determine if adjustments need to be made, compare these measurements to acceptable limits specified by the equipment manufacturer or by internal maintenance standards. Step 7. Display the corrections necessary at the driver unit's feet. Based on the parallel and angular offset measurements, the computer calculates and displays the vertical and horizontal corrections necessary at the driver unit's feet. The display will show the required vertical shimming for both front and back feet. Next, the computer will display the horizontal corrections required at the front and the back of the machine. The final step in the laser alignment procedure is to adjust the driver unit according to computer readings. To adjust the vertical alignment, insert the appropriate shims under both the front and back feet of the driver unit and tighten the bolts. The bolts should be snug with the shims compressed, but do not fully tighten them until the alignment procedure is completed. Before horizontal adjustments are made, new laser measurements must be taken because the machine may have shifted during shimming. Once the second measurements are taken, the computer can display the necessary horizontal moves. You are now ready to move the front and back of the machine in the direction shown by the display until the horizontal correction values equal 0. These moves are referred to as horizontal corrections, which has historically meant blows from a hammer. But the machine should be moved by jack bolts or other appropriate mechanical or hydraulic means. Once the machine has been adjusted, all mounting bolts should be properly tightened. Since the machine has been moved, it is necessary to take one last set of alignment measurements to verify alignment. If the measurements are within tolerance, the equipment is properly aligned. If the measurements are not within tolerance, steps 6 through 8 should be repeated. If, after several attempts, the machine cannot be adjusted within tolerances, you should look for mechanical problems with the machine, such as soft foot, worn bearings, a damaged coupling, or unstable foundations. In this program, we have reviewed some general alignment principles, introduced the principles of laser alignment, established some safety precautions, discussed the preparation of equipment for alignment, and followed the 8-step laser alignment procedure. We'll leave you with one last piece of advice.
Don't loosen too many bolts at one time.
Thanks for joining us.